In this video, you will learn how to transform a population of continuous variables by converting each variable's value to a standard normal value, or a z-score. We will then graph the results and evaluate whether it is a normally distributed population. This data set represents the entire set of 105 homes sold in a certain town last year. Therefore, we can call this a population. The sale price of a home is a continuous variable. I'm going to sort the data by price, lowest to highest. Next, I'll calculate the average and the standard deviation. Notice that because this is a population, I'm using the stdev.p, or population form of the standard deviation equation. Now that we've got the average and standard deviation calculated, we can transform the price column to a z-score. The formula for z is x minus mu over standard deviation. We now have all of those values here. X is represented by our price. Mu is the average of the population. Standard deviation is a measure of variation around the population mean. I'll set up a new column for our transformed results, and I'm going to enter the formula as equals price, which is my x, minus my average, which I will lock using the F4 key, because I'm going to drag this down the column, close parentheses, divided by standard deviation, which I'll also lock. Now that I've hit enter, you can see that the first price of $125,000 is minus 2.05 standard deviations away from the mean. We should expect a negative z-value here because price of 125 is lower than the average. Therefore, it is to the left of the mean, which results in a negative z-value. We can double-click the small square in the bottom right of this cell, and it will copy the formula down the column. Our 105 values all have now been assigned z-values. Now we can graph our results as a histogram and see how close our population is to being normally distributed. Before we do, though, let's take a look at our data. In a normally distributed population, 68% of the values fall between 1 and minus 1 standard deviations of the mean. Approximately 95% fall between 2 standard deviations of the mean, and 99.7%, or virtually all of the data, are within 3 standard deviations. Our smallest negative standard normal value is around 2, while our largest is closer to 3. So we do have some skewness in the results. To create a smoothed histogram, I'll actually use a variation of a scatter plot. The first thing we need to do is put in a column for frequency bins, because we're going to group our data between the bounds of minus 3 to 3 standard deviations. I've set up my bins for the histogram. Now I can add a frequency formula. I'll select all of the cells that I want my output to go to because the frequency formula is an array, and we select all cells where we want the output entered, equals frequency, and then it tells me that I should select my data array. I'm going to select my z values. I do not want to select the label for this. One thing you can do in Excel to quickly enter values is to click on the first cell and then Control-Shift down arrow will go to the bottom of your data set. Now I can click comma and Control up arrow to get back to the top. I'll select my bins, and instead of hitting enter, I type Control-Shift enter, or on a Mac, Command-Shift enter. All of the values that correspond to these bins are now entered into my frequency column. There are 0 values that are between minus 2 and minus 3. There are 2 values that are between minus 1 and minus 2, and so on. We can see looking at the bins, it's not a perfectly distributed data set. Now we're ready to insert our histogram, which will actually be from the scatter plot menu. I select my cells, insert, and here where it has the scatter plot icon, click the drop down arrow, and we want the smoothed one. Notice the graph has roughly a bell-shaped curve. As we suspected, there is some skewness. Some values trail toward 3 standard deviations on the right, although we have 0 for those values on the left. In this video, we have transformed a continuous distribution to a standard normal distribution and graphed the results. In this video, we'll use Excel's norm.dist function to find the probability of an area under the standard normal curve. Suppose we know the mean and standard deviation of home prices for homes that sold in a small U.S. city last year, and we also believe the population of selling prices is normally distributed. Without access to any other data, we can use norm.dist to find the percentage of homes which sold for greater than any value, for less than any value, or between any two selling prices. Norm.dist requires 4 pieces of information. I've pasted in an image of the dialog box. Let's walk through each required component. First, the x is a specified value for a continuous variable. In the first question we need to answer, x is $150,000. Next, the mean, which is our population mean, has been given to us as $221,100. Third, the population standard deviation has been given as well, and that's $47,110. And finally, are we seeking a cumulative or a non-cumulative value? True returns the cumulative probability up to and including some value. False will return the height of that x value on a probability density function. On an interesting note, given a continuous probability distribution, the probability of equaling any one value is effectively 0 because we have infinite possible values. Therefore, the probability of x less than or equal to 150,000 is the same as the probability of x less than 150,000. Let's use the dialog box to answer the first question. In the cell, I'll type equals norm.dist, open parenthesis, and then click this FX button to open the dialog box. In the dialog box, we'll enter 150,000 with no commas. For the mean, I'm going to go up here and click on the cell that has my mean, and for the standard deviation, I'll do the same, and then for cumulative, I'll say true. We can see the answer is already showing up. It's about 6.5%. Let's think about what the cumulative is telling us here. Because we are looking at a continuous distribution with values that stretch from negative infinity to positive infinity, norm.dist will return a cumulative probability from the negative infinity up to the x value that you've specified. We have about 6.5% of homes sold for less than $150,000, assuming that we have a normally distributed population. In the next question, when we're asked to answer what percentage of homes sold for greater than $280,000, the cumulative probability that we find when we put an x of 280,000 will be the probability of selling up to 280,000. To find the answer for this question, we have to subtract that probability from 100%. Let's solve it in the cell. Equals 1 minus norm.dist. And when I put the left parenthesis, it will tell me what to put, so I don't need the dialog box. My x is 280,000, comma, my mean, my standard deviation, and then true for cumulative. About 10.5% of homes sold for greater than $280,000. Finally, we want to find what percentage of homes sold for between $150,000 and $280,000. This is a 2-part calculation. We want to find what percentage of homes sold for less than $280,000, and then we want to find what percentage of homes sold for less than $150,000. When we subtract that second piece from the first piece, we'll find the overlapping area that gives us the percentage of homes that sold between 150 and 280. Again, we can do the entire thing in a single cell, equals norm.dist, and we put in 280,000 for the x, the mean, the standard deviation, true, close parentheses, minus norm.dist, the x of 150, the mean, the standard deviation. I can double click on true, and it will insert it for me. Now when I hit enter, it's going to give me the area under the curve that falls between 150 and 280, which is about 82.9%. In this set of 3 questions, we have found the probability of homes selling for less than 150, 150 to 280, and more than 280. That is the entire population of homes. When we add all 3 answers, we should get 100%. I'll select them with the mouse key, and at the bottom you can see the sum adds to 1. This video has demonstrated how to use norm.dist to find the cumulative probability of area under the curve in a normal distribution. This video demonstrates how to use the norm.inv function in Excel to find the value of an observation in a normally distributed population. In this example, a car dealer sells and leases cars. Most car leases last 4 years. The average number of miles put on the vehicles by lessees is 52,000, with a standard deviation of 5,000 miles. Lessees incur a penalty for exceeding a maximum allowed mileage during the 4 years. If the dealer has decided to set the limit so that 25% of lessees exceed that limit, what will that limit be? We will set x equal to the number of miles allowed before a penalty is incurred. I've pasted in an image of the dialog box when we use the norm.inv formula. We only need 3 pieces of information: the probability, the mean, and the standard deviation. This is a cumulative function by default, which means it will return the value which is up to and including an area under the curve. That means if I enter 25% or 0.25 here, we would be solving for the lower limit of miles driven by 25% of drivers. 25% of drivers, in other words, would drive that many miles or less. Instead, I want to know the number of miles that will only be surpassed by 25% of drivers, which, when we're using a cumulative function like norm.inv, means finding the number of miles that 75% of drivers will not surpass. Let's solve in the cell. I've typed equals norm.inv and open parenthesis. If I wanted the dialog box, I would just click the FX and the dialog box would open. But we can enter the values right here in our cell. The probability, as we've already stated, is 75%, which I can enter as 0.75 or 75 and the percent sign. The mean is 52,000 miles, which I'll type in without any commas in the number. 5,000, which again I'll type in without any commas. And I'm done. I close the parenthesis, I hit enter, and my answer is 55,372 miles. If the lease limit is set at 55,372 miles for a 4-year lease, 25% of drivers are likely to exceed that limit and incur penalties. This video demonstrated how to apply the norm.inv function to identify the value of x given the probability, mean, and standard deviation in a normally distributed population. This video demonstrates how to use Excel's norm.s.inv function to find standard normal value, and how to use norm.s.dist to find probability. If you want to know the value for z at the point which captures 75% of the area under the curve, that's easy to do when we have a standard normal table. However, what if we don't have access to a table? Excel will identify the z-value for us using the norm.s.inv function. This is an image of the dialog box that comes up when we type in norm.s.inv and hit the FX button. We only need 1 piece of information, which is our cumulative area under the normal curve. Some standard normal tables in textbooks will give area under the curve for 50% of values, starting at the mean and moving to the right. Excel starts at -infinity and gives the value for the cumulative probability up to and including some percentage. To find the z-value that corresponds to 75% of the area under the curve, enter 0.75 or 75% equals norm.s.inv, open parenthesis, and then I'm going to enter the answer here in the cell since there's only one value that we need, and the answer is 0.67. A z of 0.67 corresponds to approximately 75% of the area under the curve from negative infinity up to that value of 0.67. The size of my cell will determine the amount of rounding in Excel. If I expand the column width, I'll be able to see more decimal places. In the next problem, we want to find the z beyond which lie 10% of our values. Remember, z is a standardized value for x. Think about things like test scores. We can convert all the scores to z and find the z at which 10% of tests earned higher scores. To do that, however, we really want to find the z at which 90% are lower because it's a cumulative probability, and the answer is 1.28. Or I can expand the cell and we can see a lot more decimal places. Sometimes we want to know the cumulative percent of values captured under the normal distribution curve up to and including our z. Again, if you have access to a table, the probability can be found quickly. Excel is another fast way to get the answer. As you can see in this dialog box for norm.s.dist, we need the z-value, making sure that we use a negative sign if the z is negative, or we indicate true for cumulative. By the way, using a false here would tell us the height of the curve at that point, which is useful if you're putting together a probability density function. For finding probabilities, we use true, and it will return a cumulative result. What is the area captured under the curve, up to and including a z of 1? Let's solve it in the cell. Equals norm.s.dist, 1 and true for my values, and hit enter. So the probability, the cumulative probability of z less than or equal to 1 is about 84%. In the next problem, we're asked, what if we want to know the area between a z of -1 and 1? You probably know that answer by heart. Let's see if Excel returns the same answer. Since we have a cumulative probability function, we're going to split this into two parts. We'll find the area under the curve up to a 1, and then we'll subtract from it the area up to and including -1. The result of that calculation will tell us the space between 1 and -1. Equals norm.s.dist, 1 true, minus norm.s.dist, -1 true, close parenthesis, and the answer is 0.6827, or about 68%. This video has demonstrated how to use norm.s.inv to find a z-value given a probability, and how to use norm.s.dist to find a probability given a z-value. This video demonstrates how to use the expon.dist and gamma.inv functions with exponential distributions. In this example, the boot time for a particular computer has been found to be 27 seconds on average. Assume that boot time follows an exponential distribution. If we wish to solve for the cumulative probability up to and including a certain boot time, we can use expon.dist, which is a formula in Excel. The dialog box, which pops up when you input that formula and click the F sub x button, is shown here. As you can see, it requires three components: x, which is the value for which we're seeking a probability, lambda, which is 1 over the mean, and cumulative, which can be true or false. True returns a cumulative probability up to and including the value of x. False returns the height of the probability density function at that x value. Let's find the probability of a boot requiring less than 15 seconds. That is, the probability of x less than or equal to 15. Equals expon.dist, open parenthesis, and then I'll click the F sub x button to open the dialog box. For the x, we'll put in 15 since we're trying to find the probability of it requiring 15 seconds or less to boot. For lambda, we put 1 over the mean, and for cumulative, we'll put true. And you can see already that it's showing me that the answer is about 42.6%, or 0.426 is the probability of requiring less than or equal to 15 seconds to boot. The next question asks, what's the probability the next boot requires more than 60 seconds? If we enter 60 for our x, we're going to find the probability up to 60 seconds. That is the probability of requiring less than 60 seconds. And so in order to get the probability of greater than 60 seconds, we'll do equals 1 minus exponent.dist. And I'll solve this in the cell. My x is 60. 1 over 27 is my lambda, 1 over the mean, and then true, close parenthesis, and the answer is 10.8%, or 0.108 is the probability the next boot requires more than 60 seconds. How about the probability that the next boot requires 30 to 45 seconds? This requires two calculations, both of which we can do in the same cell. If we find the cumulative probability of boots taking less than 45 seconds, we can then subtract from it the probability of taking less than 30 seconds, and the remaining area under the curve is the probability of a boot requiring 30 to 45 seconds. So we'll do equals exponent.dist, and for the x we'll put 45, 1 over 27, true, and then subtract from that, exponent.dist, 30, 1 over 27, and true. And it's 14%. Approximately 14% of the time, it will take between 30 and 45 seconds to boot. What if you wanted to find out the value for x given a probability of occurrence? In Excel, we will use the gamma.inv formula. It requires the probability, which is always cumulative, an alpha value, which is 1 when we're using the exponential distribution, and beta, which is the mean of our exponential distribution. So it's a simple formula to use in Excel. Here we're asked for the time below which 10% of boots will occur, equals gamma.inv, open parenthesis, and the probability that we're asked for is the probability in seconds below which only 10% of the boots occur. So we are looking for a probability of less than or equal to 10%. Alpha is always 1 when we're using the exponential distribution, and the beta is the mean. 10% of boots will take 2.8 seconds or less. The next one says, what is the maximum time beyond which only 10% of boots occur? Well, if we want to do this as a cumulative probability, which is what the gamma.inv function is, what we really need to find is what is the limit below which 90% of boots occur, because that's also the point at which 10% require longer than that time period. So equals gamma.inv, and 0.9 for the probability. The alpha is 1 and the beta is the mean of my distribution, and that's 62.17 seconds. Remember when we solved for the probability it would take more than 60 seconds for a boot to occur? Almost 11% of boots will take 60 seconds or more. Here, 10% of boots will take more than 62.17 seconds. This video demonstrated how to use exponent.dist to determine probability for an exponential distribution, and gamma.inv to find x for an exponential distribution when given probability.